Next, I invite Basudeb Dasgupta from TIFR, and he'll tell us about neutrinos and dark matter.
My name is Basu. I am from TIFR. I'm a theoretical physicist. I work on theoretical aspects of neutrinos and dark matter. I am what one would formally call an astroparticle physicist or a particle astrophysicist, depending on which continent you got trained in. And you'll see why I'm mentioning this, because what I'm going to talk to you about is how to use this interplay between particle physics and astrophysics to learn more about particle physics and astrophysics. You know, there's more that you can do when you combine these two fields of particle physics and astrophysics. And an underground facility, especially the one we are asking for in India, would really go a long way in helping us do that. Okay, so particle astronomy is different from astronomy with light. And the key thing that we're trying to target is to look very deep into stars and other objects. You know, we want to study what's happening inside stars, inside the depths of galaxies and so on. But those parts of the universe are so dense that even light cannot escape from there. This is not because there's a black hole or anything there, but the refractive index can be so large that light just gets trapped. So light doesn't escape. Or that light keeps scattering around, it never escapes. Just like, you don't see behind a cloud. The same thing's happening all over the universe, and we are not able to collect this valuable light from a large part of the universe. However, weakly interacting particles like neutrinos and dark matter do not suffer from this problem. Right now, about 1 billion neutrinos are going through each, like square centimeter every second, from the sun. And we don't even know. So these neutrinos can go all through us and everywhere else, and they're coming to us from the depths of stars and galaxies. And they carry a lot of useful information. We would like to be able to capture these neutrinos and dark matter and these kind of weakly interacting particles and learn more about the rest of the universe and about these particles. These particles, because they're coming from these very deep parts, they're also probing extreme conditions in the universe that you cannot create on Earth. High temperatures, high pressures, large magnetic fields, and so on. And there are, of course, things like dark matter which just do not emit sufficient amounts of light, in principle. So if you want to study the physics of dark matter or something, the only way that you have with you is particle astronomy. Now, the same reason that particle astronomy even works, the fact that these are very weakly interacting particles, also makes particle astronomy very hard, because they pass through the star. How would you even detect them? That you need a very big detector, and your neutrinos and dark matter would just pass through your detector. So how do you even detect it? So the trick is that you build as big a detector as you can, and you wait as long as you have to. So there are a few interactions that will happen over a sufficiently long time. And typically, depending on the experiment, you have to wait 1 day for one event, sometimes 1 year for one event. So these can be hard measurements, and that is precisely why you need to go underground. Because we are constantly being bombarded by cosmic rays, which are basically disturbing your detector. And if you go underground, you reduce this external particle noise exponentially. So here is a plot that tries to show you this. On the x-axis here is the vertical overburden, So it's in water equivalent, so meters water equivalent. So 7 kilometers of water, that's about 1,500 or like 1,200 kilometers of 1,200 meters of rock or so. And then on the y-axis is the flux of muons, but that's on a log scale. And what you see here is roughly a straight line going down that tells you that the muon flux is dropping exponentially as you go down linearly. Okay? And there are these observatories all over the world. You can see the names here, but there's not one in our country. There used to be one in the Kolar gold field, which made tremendous discoveries, including the first atmospheric neutrino was discovered there. But we don't have one now. We would like to have one. And I've already told you that the reason why we want to have one is because it's a quiet environment. It's a particle quiet environment, just like how Arjun told you about a seismic quiet environment. We care about a particle quiet environment as well, and that's where an underground lab comes in. Okay, so in the rest of my talk, I'm going to give you examples. I'll give you 2 examples from neutrinos and 1 example from dark matter. These are 3 projects that in principle we could do in India, which target neutrinos of high energy, neutrinos of low energy, and dark matter. And we could learn a little bit more about these particles and about the astrophysical sources that send us these particles. So neutrinos, I imagine most of you have heard about neutrinos. These are fundamental particles. And the coolest thing about them is that they have a very interesting quantum mechanical behavior. That there are 3 kinds of neutrinos, E, mu, tau, but then they transmute into each other as a function of time. So if you have an electron neutrino, it can become a muon neutrino, and then it keeps oscillating back and forth. This is called neutrino oscillations. This has been a field of intense activity over a few decades. And a huge progress has been made. Several people have won Nobel Prizes over the last few decades. These are examples of some big detectors. So for example, this is IceCube, and what you see here is just an event display shown below the Antarctic ice shelf. So this is about 3 kilometers deep, and what you see above over there, that's the above ground processing centers, if you will. Here, this is a huge tank of very pure water in Japan, and then it's instrumented from within by photomultiplier tubes looking inwards. So when a neutrino comes from outside, it interacts in the water inside this big tank, and then it produces muons, for example, and then you can detect the light from these muons using these PMTs. And what you see here, that's a little boat with graduate students polishing those PMTs. So that's how big these detectors need to be. Okay, so these are about, so the IceCube is about 1 kilometer cube of instrumented ice. This is several tens of meters on each side. So these are big detectors. They're all underground. And we've made huge progress, but there's basically a whole menu of things we would like to learn. And these are fundamental problems. For example, neutrinos are presently the only particle in the standard model, the only fundamental particle in the standard model, for whom we do not know what mass it has. Okay? So Higgs boson was discovered about a decade ago, and it's one of the particles whose mass we know most precisely. But neutrinos, we don't know what its actual mass is. We know something about its mass. We know the difference of the squares of the masses, but we don't know the mass. We would like to know that. There are other things. For example, there are 3 neutrinos, so they have 3 masses. We don't know what ordering they have. We don't know if there is CP violation, which basically tells you whether you can have more matter than antimatter or not. And we see that there is more matter than antimatter in the universe. There are other questions associated with neutrinos, and we would like to pursue these really, really important fundamental questions. And neutrino astronomy gives you a way to pursue these questions. So the first example, using high energy neutrinos. So these are neutrinos that are produced when cosmic ray particles interact with air molecules in our atmosphere, and then they produce pions and muons. These are unstable particles which immediately decay, and then they make neutrinos. And so we are being, so these neutrinos are raining down on us from above and from below, because on the other side of the Earth, also cosmic rays are interacting, and these neutrinos which are produced there are not interacting strongly enough, so they go all the way through Earth, and they come to us from below our feet. So we are being bombarded by these neutrinos, these atmospheric neutrinos from all directions, and we would like to detect them. So the interesting thing about these atmospheric neutrinos is that they first of all come to us from a wide variety of distances. basically, on the horizontal side, like meters, tens of meters, and on the vertical side, because from the other side of the Earth, so like 10,000 kilometers. And they have a very large energy range as well. This large dynamic range of energies and distances allows you to make very precise measurements of this neutrino oscillation, this quantum mechanical change of flavor. And it's using these that we know that neutrinos have mass and that neutrino oscillation does exist in nature and so on, but we can do much more. Another interesting and really cool thing, which is very sadly underappreciated, is that neutrino oscillations of atmospheric neutrinos is the largest macroscopic scale quantum coherence ever seen in nature. We're so excited about quantum mechanics and quantum physics these days, and people are trying to do these really amazing experiments of trying to send photons up to a satellite and bring them back, and they set records that, okay, we've established coherence, quantum coherence over a few hundred kilometers, maybe 1,000 kilometers. These are coherent quantum mechanical processes over 10,000 kilometers. So nobody's beaten neutrino physics on this account yet. So this is very interesting stuff, and there is a really, really, broad and long-term science case for these atmospheric neutrinos, because many of these measurements just are going to take a long time. You'll need decades to collect enough data, and that's precisely what motivated INO or ICAL's science case. That science case still remains; it's not gone anywhere, and India actually developed quite a good experimental capability to address these questions. In particular, these oscillation studies. And now I'll quickly pivot to these neutrino-based Earth tomography as an example, just to connect to Arjun's talk. Okay, so these neutrinos, these high-energy neutrinos from the atmosphere come to us from all possible sides, and depending on their energies, you can either use absorption or neutrino oscillations to study the Earth using them. So I'll not have much more to say about that, but you can speak to many people in the audience, like Amol or Sanjeev, who will tell you more about that. One of the interesting things that they showed recently is that you can measure the location of the boundary of the core and the mantle to within a few hundred kilometers using these atmospheric neutrinos. Of course, you need quite a lot of data. You need decades of data. But this wouldn't be possible in many other ways. Okay, so I move on to my second example. So I was talking about high energy neutrinos. These were of order tens, maybe hundreds of GeV. Now I move to neutrinos which are at lower energies, or tens of eV. These are neutrinos that are not produced from decays of these pions or kaons, but rather in nuclear fusion reactions, which are occurring in stars. So these are much lower in energy. And these neutrinos are also useful to study oscillations and to study whether neutrinos have mass and what mass they have and so on. What I'm showing you as pictures here, this is very cool. This picture is actually a picture of the sun, but not taken using light. This is a picture of the sun taken using neutrinos, because the detector can tell which direction the neutrinos came from, and then it reconstructs an intensity map of where the neutrinos have come from, and that's the picture of the sun, false colored, of course, and that's a picture of the sun in neutrinos. This is a picture of the supernova that happened just outside of our galaxy in 1987. That's the last core collapse supernova near our galaxy. And this is a hand-drawn plot of the neutrinos that were observed. These red scratches are each event. So of course, we can do far more sophisticated things than this these days, and we hope we will have an opportunity to once we have a neutrino detector here. So what we are proposing to address this stellar neutrino aspect is we build a new kind of detector called a deuterated liquid scintillator detector. The key word is deuterated. Deuterated means that all the hydrogen is replaced by a deuterium, and deuterium is a proton and neutron. Hydrogen is just the proton. Once you have both proton and, so it's a isotope. So once you have both the proton and the neutron, you become sensitive to all the neutrino flavors. You become sensitive to electron neutrino, its antiparticle, the electron antineutrino, and then the muon neutrino, the tau neutrino, and their antiparticles. So there are 3 flavors and their antiparticles. You can detect all of them. Okay? And you can do that at MeV scale energies. You can also tag them. It helps to reduce background. You can also measure their energies very precisely. And with that, you can do very interesting stellar physics. There are, of course, significant challenges, but this is a truly unique opportunity because India is the largest producer of heavy water, which is relevant for our nuclear reactor program. And this heavy water is an incredibly expensive resource, which almost no other country has access to because, first of all, they don't have any. Whoever has any, they wouldn't be able to, so you can't buy it. It's just so expensive you can't buy it. But in India, because DAE produces it, there is perhaps a way of having this heavy water on loan. Because we don't destroy it in any way, we can give it back if we have to. And maybe that's one of the ways you can build a detector using this very interesting thing, deuterium, which becomes sensitive to all neutrino flavors. So I'll skip this slide. Basically, all it says is that a deuterium-based detector has spectral and tagging information in all flavors, which you don't get. So all these ticks that you see for the DLS tell you that it outperforms any other detector concept. Okay, and this is an example of what it can do. Is that if you look at neutrinos from the sun, it can first of all lower the threshold from 5 MeV to about 2 MeV, because now we are talking about a scintillator, which has much lower thresholds, and you see about 300 events per 1,000 tons per year, which translates to this red data point, which currently does not exist. And with a 6% precision, you pin down the shape of this gray curve, which is the currently accepted theory, but there is really no data that truly tests the most important part of that curve, where it changes. But DLS can do that. Okay, so let's move on. If you have a supernova in the galaxy, the DLS detector will detect all the flavors with energy spectrum. This would be unique. No other detector can do this. And we've been working on it for a couple of years, but perhaps the most important thing to tell you about it is that at BIRC, Prakash, who will speak after me, has built a very small prototype of one of these deuterated scintillator detectors, and here you see its light response and so on, and he can tell you more about that. But we are very far away from building the big detector because this is a really small prototype. Okay, in my last 1.5 minutes, I'll tell you about dark matter and what you can do about dark matter from an underground science lab. So we've all heard about dark matter, this mysterious mass in the universe that does not shine in light. We know that it exists because we have measurements of masses of these astrophysical objects, and that does not agree with the observed mass. Okay? So we know that there is this mass which we don't know what it's made of. It's not made of atoms, that we know for sure. So it's something beyond the periodic table. Okay. And there's a worldwide effort at trying to figure out the nature of this dark matter. This is really one of the frontier problems of modern physics. And it's really cool that there is an experiment in India. So this is an experiment that's led by Mala Das from Saha Institute of Nuclear Physics. This bottle, if you see, this green bottle, it contains a superheated liquid. And what it does, it waits for one of these dark matter particles to come to you. As it passes through the bottle, it creates a little bubble, and then the bubble expands and creates a sound wave in your detector, if you will. This is picked up by piezos that are on the outside of your detector, and you record it. Again, you need to be deep under the ground so that you're not being bombarded by cosmic rays all the time. So this is the detector concept. So they've been running this detector for a while now, and they already have interesting results. So this red line is basically telling you that they've not observed dark matter, but as a result, they can tell you that dark matter above a certain interaction strength and mass does not exist, and so on, and they can do much better. This dashed line that you can see over here is what they can get to at their current location, and that's already very interesting because there's interesting parameter space to be explored. But more importantly, they're currently at this site in Jadugoda, which is at a depth of about 500, and they can maybe go down to about 800, but this place is very small, so they can't grow very much. This is very cool that we have this, and we would like to maybe go all the way up here. But what would be really cool is if you can go to an underground science facility about 1 kilometer, maybe a bit more than 1 kilometer deep, and then you get this humongous improvement in the sensitivity of your detector. It's like 3 orders of magnitude or something, maybe more. I think it's about 8 orders of magnitude. So that would be really cool. I think my time is up, and I'll end up with my summary. So we can do astronomy with weakly interacting particles if we are willing to go underground. There's very interesting physics associated with neutrinos, dark matter. I didn't tell you anything about axions. There are interesting projects already in the works in the country. There are people excited and capable of delivering you this science. And there's synergy with a lot of other fields. We heard about seismology. We'll hear about nuclear astrophysics. There's seismology with gravitational waves. There is synergy with gravitational waves that I didn't speak about. And so I invite you all to contribute to the science case.